Hello all. So we're back once again with our live streams, and today we're going to talk about generics. And yeah, here they say in, out, and where. And if you haven't already, please subscribe to the channel if you'd like to know more about Kotlin. And in this course, we talk about Kotlin in depth from start to end, and we read all the documentation. So if you haven't already, you can subscribe and also enable the notification bells to know when I will live stream again. So let's start with the classes in Kotlin. Kotlin, yeah, they can have parameters just like in Java. And to create an instance of such a class, you simply need to provide the type arguments. So, for example, in this case, we create a class box with type parameter t, and then we have an initializer with a parameter t, which is of a generic type t, and then we instantiate a value with the parameter t, sorry, a variable with a parameter t. And as you see, when it can then create a class of such a, an instance of such a class with this simple syntax in which we state which is the type of the parameter we want to pass, which is in this case integer, and then we pass the integer type. And then if we want, we can also infer the type integer this way. So we just pass in the value directly, and the integer type in this case will be inferred from the argument that we're passing. So let's try this out. Let's play with generics, and we just create a function here, and we say value box. And of course, we need to create a box. So let's do it right here, box. And we say box.pt, and we have class box. Then we need to provide a type parameter t, and then we say that we have an argument t of type parameter t, and then we say we have a variable value of type t, and then this is going to be equal to t. And we're good to go with our class. Then we instantiate it with integer type, and then, sorry, we just say instantiate it this way, integer and type. Parameter is going to be 1 of value 1. Okay, and we're good to go. So as you see here, we can remove the explicit argument since it's already known at compile time. And we can have also box2 directly equals to this. And as you see here, it will be inferred directly by the parameter that we're passing. Of course, if we say long, then the box is going to be long, and we're good to go. Then let's go on. So one of the trickiest aspects of Java type system is wildcard types. See Java generics, frequently asked questions. Okay. Kotlin doesn't have these. Instead, Kotlin has a declaration side variance and the type projections. So variance and wildcards in Java. Let's think about why Java needs these mysterious wildcards. First, generic types in Java are invariant, meaning that a list of string is not a subtype of list of objects. So if list were not invariant, it would have been no better than Java's arrays, as the following code would have compiled, but caused an exception at runtime. So if we have a list of strings in Java, we have a list of objects, which is going to be equal to the list of strings, and here we will have an error at compile time. What if we didn't? We wouldn't be able to put an integer into a list of strings. So we try to have an object, add 1. This is an integer, cannot be happening because this was a list of strings, so that would make issues later. And then at runtime, Java would throw a class cast exception. Integer cannot be cast to strings. So yeah, we would be able to do that, but at runtime, we would have an issue. Java prohibits such things to guarantee runtime safety, but this has implications. So for example, consider the add-all method. What's the signature? Intuitively, you'd write it this way. So we have a collection of type elements, and we add all elements of type E, so of one type. But then you would not be able to do the following. So copy a collection of objects to a collection of strings, because we don't know if the collection of objects are all strings. So the following would not compile with native declaration of add all, because yeah, as we said, the collection of strings is not a subtype of collection of objects. So that's why the actual signature of add all is the following. So it's a little different here. You see, we have an interface, collection E, void add all, collection E, yeah, some type extends E. Yeah, so the type is actually extended. It is extended from not, yeah, we don't specify the types directly in the add all signature as we do here. So the wildcard, yeah, the wildcard type argument indicates that this method accepts a collection of objects of E or a subtype of E. So not just the E itself, like we were doing here. This means that you can safely read E from items. Elements of this collection are instances of a subclass of E, but cannot write to it as you don't know what objects imply with that unknown type of E. In return for this limitation, you get the desired behavior. Collection of string is a subtype of extends object. In other words, the wildcard with an extends bound makes the type covariant. The key to understand why this works is rather simple. If you can only take items from a collection, then using a collection of string and reading object from it is fine. Conversely, you cannot put items into the collection. It's okay to take a collection of object and put string into it. Yeah. In Java there is which accepts string or any of its subtype. Okay. The latter is called contravariance, and you can only call methods that take string as an argument on a list of strings of superstring, add string or set in string. If you call something that returns t in list, you don't get a string but an object. Okay, so yeah, it explains he gives the name producers to objects you can only read and consumers to those you only write to. Okay, that being said, if you use a producer, say a list of extend full, you're not allowed to call add or set on this object, but this does not mean that it is immutable. For example, nothing prevents you from calling clear to remove all elements, since clear does not take any parameters. The only thing guaranteed by wildcards is type safety. Immutability is a completely different story. So declaration site variance. Let's suppose that there is a generic interface source t that does not have any methods that take t as parameter, only methods that return t. Then it would be safe to store a reference to an instance of source string in a variable of type source object, like they're doing here. There are no consumer methods to call, but Java does not know this and still prohibits it. Yeah, so this is not allowed. To fix this, you should declare object of type source extends object t. So here, yeah, you would need that. And doing so is meaningless because you can all the same, yeah, because you can call all the same methods on such a variable as before, so there's no value added by the more complex type, but the compiler doesn't know that. In Kotlin, there is a way to explain this sort of thing to the compiler. This is called declaration type variance, and you can annotate the type parameter t of source to make sure that it is only returned from members of source t and never consumed. To do this, you can use the out modifier. So from members, yeah. So you can annotate the parameter t to make sure that it is only returned from members of source t and never consumed. So this case, we are returning type t and it is not going to be consumed. And we can specify it with out modifier. Let's try this. We can create our source source.kt. Then we have our interface with out t, and then we return next t. And this is going to be fine. Yeah, this is going to be fine since t is an out parameter. So we're passing source of strings, value objects, source any equals to string. So let's try our function Conditional. Then we have our strings, source of strings, import this. And now we create our objects. So yeah, we can specify source of any, and then we have our source string. So this is going to be fine. Source of string. Yeah, we need to specify an implementation for this. And we need to have in the top level declaration. Let me fix this. So yeah, this needs to be specified here. We'll see this in a few moments, I think. And members. Okay, I need to have also the. This class does not have a constructor. Remove it. So we need next element. So next is going to be all elements of next. What it might be. Let's start with val index 0, and then we have it e, and then we increment e. So this is going to be a variable. Wait, it has to return that in factor. So so we're going to return the stored element inside the all elements list. And of course, we would have list of elements. What's happening here? Expecting like let's do like this. And, oh, B, and then we add. We say this equals to. And we make it a variable. So yeah. Split init. Okay. So we call this init elements. So let's try to have our source implementations. So now we pass in our source implementation. So this, and then we have list of this, and we import. Too many arguments. Okay. Yeah. This should be here. So we have sources. Yeah, we have this. We have string. Now we're good. Now, all elements of init elements, right? Then we pass in sources, implementation. Let's see what happens now. Yeah, it's printing the objects, source any, and this is going to be okay. But what if we convert it to a source of string? I want this. Change type arguments to these. Oh, yeah, but I really want these to become like things copy, and then we call it like this, or it's not string. Yeah, this is going to be, yeah, as you look here, we have some issues. If object is source, check typecast. Remove useless check. This is probably some warning. Let's copy these here and let's run it again. Yeah, as you see, it's going to have a warning unchecked cast of type any to string. So this is there is some issues, as you see, because the checking cannot be casted anymore, cannot be checked anymore. And this is very strange. Let me check. So what is the problem in this code again? Let me check it again. So what we do here is subtyping is preserved. So this is allowed. Because we are using out in source string. So in our source, we're using out. So this means that can cast it to source any. That's the reason. So T is a covariant type parameter. That's what we have now. So you, and what else? You cannot do this. So you cannot pass it as parameter. For example, pass me T. As you will see here, the type parameter is declared as out, but of course in position int type T, so it cannot be used safely. So I would need to add unsafe variants, right? So I just say not allowed here, and we're good to go. And then this ensures safe variants in Kotlin type system. So this is everything you need to know. What if we remove the out? Then we would not be allowed to do this. Type is match, inferred type is source string, but source any was expected. And this is because the source string and source any cannot be treated as compatible types in this case. All right. So this is useful when you design an interface that needs type t as return type for its function. Okay, that's it. Then let's go next to our in, I believe we have here. So yeah, let's read what I have here. The general rule is this: when a type parameter t of a class C is declared out, it may occur only in the out position in the members of C. But in return, C base can be safely derived from of C derived. In other words, you can say that the class C is covariant in the parameter T, or that T is a covariant type parameter. You can think of C as being producer of T and not a consumer of T. So C is a producer of T and not a consumer of it. In this example, the out modifier is called variance annotation. And since it provided at the type, it is provided at the type parameter declaration site, it provides declaration site variance. This is in contrast with Java use site variance, where wildcards in the type usages make the types covariant. In addition, out Kotlin provides a complementary variance annotation, the in. So this is the complementary annotation, and it makes a type parameter contravariant, meaning it can only be consumed and never produced. A good example is the comparable. So the comparable can only be inserted as input to the functions of the interface, and they can be used as outputs. So comparable, let's bring our comparable here. Comparable is comparable. Copy. Probably we need to rename this. Okay. Now let's make the interface comparable, test comparable, and then test comparable. We just create oops. So we can use play with generics, and then we can we can have our implementation of this. Yeah, this demo. I think we'll need an implementation of the class. Otherwise, it would be difficult to pass in a comparable. Class. Okay, so T, and we have this as our members, compare T to other I don't know, which we can just say back to t. So what we might do is we might have our a here. Yeah, it's not even allowed inside this. That's interesting. Inside the arguments of the constructor. So let me think. We need we have other, but what are we comparing it to? That's the thing. Does it make sense? X compared to 1. Yeah, but X is a comparable number. So it's a comparable integer. And how did we pass it? I'm trying to figure out some way of maybe passing some type. And maybe like that it works. So yeah, well, so it's going to be unsafe variance. How can we create a class in passing a parameter of type t now? Aha, baby, because I have placed this as in. So maybe first, maybe this way it works. Yes, because then the interface has its functions that want the t as input to the functions and not as output. And this way it works. So I was forcing this to be an input only. Yeah, an output only or an input only. I don't remember. Yeah, an input only probably. And this was failing because of that. So now this should work out. Yeah. This is not working because, yeah, we need to compare them in some other way. I don't know what to do here. Maybe if first is a subtype of integer and other is integer, and we return is greater than other as things. All right, where was it now? Oh, yeah, we should have compared to, but if I don't remember what the compared to does, but we can do something like this. So if first is greater than other, then it returns 1, else it returns 0. It's just our comparable function, how it will work. Let's try it out in practice. So we pass in test comparable implementation of integer. Then we have our integer here. First of type t. Test comparable number. So body ones. What's expected? Yeah, this way it works. Can we compare it to 1? Maybe we say 2. Okay, test double was expected. Yeah, because here we had number. We had number before. Just comparable number was expected. Check the cast. Let's try this. Yeah, unchecked cast. So we have 2 warnings here when we do this. Let's try and print this. Comparing. Maybe we should place 1. Let's see what happens. With this. Let's run this. Okay, we have comparison 1, so the function is behaving properly as we developed it. Then we could create a comparable, test comparable double and assign x, because x is a number, so number 2 is a number, and it will contain, let's try and print it. So test comparable, let's override, yeah, override string function. This will have our in type. Oh, should override it here. First, remove curly braces, and let's run this. Yeah, comparison 1, 2. We need print line, both here and here. So, well, this is working because we have converted that comparable to double by doing this. So it has been casted from integer. First, the first argument 2 has been casted from integer to double. And double check this also by printing the type. So let's try and do I call yeah, probably not very easy to print the type in case it's going to be a generic. Let's try. Okay, we don't know how to do it, but so we'll go on. Okay, let's go on with type projections. We're still a long way to go. So it is very easy to declare a type parameter t as out and avoid trouble with subtyping on the use side, but some classes can't actually be restricted to only return t. A good example of this is array. So let's see, we have array of type t val size, and then we have integer. So this is the size of the array, and then we have a getter and setter. We can get a value of the array by giving it the index and returning the type, the object of type t, and then we have a setter with index, integer, and value of type t. So we have both an in and out, let's say. This class can be neither core or nor covariant in T, and it imposes certain inflexibilities. So consider the following. From array any to array any, we need to assert that from size is equal to the to size, and this is going to be okay. And for if I from indices 2 equals to from I, so this is a copy of one array to the other, and this function is supposed to copy items from one array to the other. Let's try to apply it in practice. So we have an array of integers, 1, 2, 3, and I'm sleeping. And val any is going to be an array of any of 3 items, which will be empty strings. We try to copy integers to any, but the type array integer, type is array int, but array any was expected, so this should be not possible. Array of type t is invariant in T, and so neither array integer or nor array of any is a subtype of the other. So they cannot be considered. The array of integers cannot be considered subtype of the array of any. So this is because the copy could have unexpected behavior. For example, it may attempt to write a string to from, and if you actually pass an array of integer there, a class exception will be thrown later. So to prohibit the copy function from writing to from, you can do the following. So you can say out any. That's interesting. So any of any, if you do out any, then this is type projection, which means that from is not a simple array, but it is rather restricted projected one. You can only call methods that return the type parameter t, which in this case means that you can only call get. This is our approach to use side variants, and it corresponds to Java array extends objects. While being slightly simpler, you can project a type in as well. So, for example, fill in the destination array with input strings and value string. you can only pass an array of string, char sequence or object to the field function. That's what it does. So let's try this. Give me a second. So let's try to copy from one array of strings to another array of any. And let's do it here. So let me create a function. Then we can create copy.pt. Okay, this is our function that we just, it's just the same as this one, just without the assert. It is saved because 2 is an array of any. So 2 is an array of any and array without any. So this means that we can only output any in the from array. And let's now have source and the destination in order to use this copy. So now let's do about source array of strings, and then we have array of, and here we have hello world, and then we have a destination. But this time, this is going to be an array of any, and this array of any can be anything like 1, 2, 3. And then we want to copy from array, so from the source to the destination, and then we'll print line the destination. We need to import these from generics. Perfect. Let's see what our printing will do. So yeah, as you see here, we'll just print the object because we need to join to string this object. And now we're going to have hello world 3. Wow, nice. So as you can see, we are joining to string the objects of any, and 1 and 2 are going to be hello and world, and number 3 wasn't changed because we are copying from index of the from to the index of 2, and we're skipping the last element because the size here is smaller. So in this case, since it's an integer, it's going to be safe to call the join string and to have our output in here. Okay. And join to string is going to be separated by the comma, as you see here. Good. So this is our example of the copy. What if we remove the inside the copy, the out? Let's try it. As you see, type mismatch. Inferred type is array of string, but array any was expected. Damn. Let's see. Yeah, as you see here, this class can be neither array of type T is an invariant in T, and so neither array of integer nor array of any is a subtype of the other. So this cannot happen because we need the out here. We need to say we're not going to be changing. We're only using it as output. We're only using the from as output of the copy function. Okay. Next. So just as a note here, from means that from will be read only. All right. Next. Star projections. All right. Ooh, still have so much left. So sometimes you want to say that you know nothing about the type argument, but you still want to use it in a safe way. So you don't know about the type argument, but you want to use it in a safe way. The safe way here is to define such a projection of the generic type that every concrete instantiation of that generic type will be a subtype of that projection. So Kotlin provides the star projection syntax for this. So we have our pull out the upper, so the upper, where t is a covariant type parameter with the upper bound, the upper, and then we have foo, which is foo star, which is equivalent to foo out the upper. This means that when the t is unknown, you can safely read values of the upper from foo. So if we don't know t, we can read values of the upper from foo. Star. So for if foo in when t is covariant, where t is covariant type parameter, foo star is equivalent to foo in nothing. This means that there is nothing you can write to foo in a safe way when t is unknown. Okay, well, it's best to have samples on this, but for foo t type where blah blah blah, let me. So this means that function in nothing string function int star. If you don't know, if you don't know anything about the outputs or inputs, you can put a star. That's what it does. Let me just unknown type. So that's going to be used for unknown types, as we just said. Okay, let's go to generic functions. We have already seen some of them, but classes aren't the only declarations that can have type parameters. Functions can have them too, and they're going to be placed before the name of the function. I think we've seen them already. No, we didn't. Sorry. So you can have type D directly inside the function. Singleton list. the basic to string, so it can also go inside extension functions. Okay. Let's maybe singleton list item t. List of t, it returns a list of t. Yeah, I imagine what this does is just it takes the item and returns it inside a list. So list of items. And let's try and do this. So the advantage here is that you have a generic type T, and this will work with any list you want, like string, integers, and so on. So meanwhile, list of generics. So like this is allowed, and this is allowed for singleton, this, and then just run it. So as you see here, we're printing singleton lists in an easy way. Then we can have basic to string. For example, if we want a particular syntax, maybe in this case we make it a little bit different. And we pass t. T is already a generic, so we can pass a list as well. And let's do this. So if t is list, if this is list, I would say, then return list of, and then this. Let's do this just for fun, and then else return this. Okay, so basic to string. Let's try and call it here. And I think we didn't do input these. This should have list of at the start of it, and we're good to go. If we just pass something that is not a list, like a string directly, a string, it will just print out a string without brackets and list of. So this works. Okay, that can be inferred. Okay. Generic constraint. The set all possible types that can be substituted for a given type parameter may be restricted by generic constraints. Let's have upper bounds. The most common type is an upper bound which corresponds to Java extends. So we have our upper bound. We need comparable T as upper bound. And yeah, the type specified after a colon is the upper bound, as you see here. So you need to pass something that is comparable inside this sort function. Otherwise, the comparison, the sorting cannot work because you must have a comparable in this case. Otherwise, how can I say if one is greater than 2 and 3 and so on if I don't have comparables? Then we can have list of hash map integer string. Yeah, this is not comparable, so it cannot be working. Let's try this just for bring by. So sort list of one import from Java. Then we try to import something that is not comparable. The doop, 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 doop. I'm generating some types that are not comparable other than the map. Maybe you need nothing Boolean. Yeah, Booleans are not comparable apparently. All three. Let's see what happens. Run these. Oh wait, it's actually running. Yeah, the sorting doesn't return the types. It's kind of strange. It does not return types. That's bad. So we would need to create a list. Each one, sort A, and then print A. And this is going to work. Don't think so. But why this returns a unit? I'm not understanding why is it returning. Yeah, this is not a way to have the sorting. I mean, they're just showing it because we have the comparable T here. But actually, the way to sort a list is to have sorted here. So, and then sorted, yeah, it takes a comparable T, and T needs to be a comparable. And this will work. So what if we try and do sorted here? This should, yeah, it's working. Here it was saying that booleans are not comparable, but I think they are. So probably just let's stick to the map of integers. Like that. That's what is it? Integer string. Here we need a map. Map. Integer. What should we have here? Yeah. As you see, unresolved reference sorted is not available, and we cannot use it because it's not comparable. Okay. The default upper bound is any. In this case, only one upper bound can be specified inside the angle brackets. If the same type parameter needs more than one upper bound, you only need a separate where clause. Okay, so you can have the where clause where T is a char sequence and T is a comparable T. That's nice, but we're not going to make this example. Definitely non-nullable types. So to make interoperability with Java, Kotlin supports declaring a generic type is definitely non-nullable. To declare a generic type T, declare the type with at and any. Non-nullable. Okay, so you can have a non-nullable with and any. So for example, T and any. A definitely non-nullable type must have a nullable upper bound. The most common use case for declaring definitely non-nullable type is when you want to override a Java method that contains not null as an argument. For example, consider the load method. So we have this load method, and you want to have something similar here. And to override this, you need to pass in xd1 and any, and this will make it not nullable. Will make the t1, so the type parameter 1 not nullable. Okay, type erasure. We're almost done, guys. So the type safety checks that Kotlin performs for generic declaration usages are done at compile time. At runtime, the instances of generic types do not hold any information about their actual type arguments. The type is said to be erased. For example, the instances of foobar and foobuds question mark are erased to just foo. So yeah, generic types, type checks and casts. Due to the type erasure, there is no general way to check whether an instance of a generic type was created with a certain type arguments at runtime, and the compiler permits such checks such as int is in list or list is in t. However, you can check an instance against a star projected type. So for example, something is a list of star. The items are typed as any question mark. Similarly, when you already have type arguments of an instance checked statically, you can make an is check or cast that involves the non-generic part of the type. Note that angle brackets are omitted in this case. So you have list, mutable list of string, and if list is an array list, similar to smart cast to array list of strings. Same syntax, but with the type argument omitted can be used for casts that do not take type arguments into account. Okay, let me check here. The type arguments of a generic function are also only checked at compile time. Inside the function bodies, the type parameters cannot be used for type checks and typecasts. To type parameters foo as t are unchecked. So the only exclusion is inline functions with ratified parameters, which have their actual type arguments in line at each call site. So this enables type checks and casts for the type parameters. However, the restrictions described above still apply, for instance, of generic types used inside checks or casts. So for example, in the type check arg is t, if arg is an instance of generic type itself, its type arguments are still erased. Okay, this is something more complex regarding the use of rectified. Think we're not going to go further with that. Unchecked casts. So the typecasts to generic with concrete type arguments such as foo as list of string cannot be checked at runtime. These unchecked casts can be used when typesafety is implied by the high-level program logic but not deferred directly by the compiler. So see this. A warning appears for the cast in the last line. The compiler cannot check fully if it at runtime and provide no guarantee that the value in the map are integers. To avoid type unchecked casts, you can redesign the program. In the example, you could use dictionary read of type V and dictionary write interfaces with type-safe implementation for different types. Okay. So there is always some ways to avoid not having unchecked casts, and you should use those ways in your code. So underscore operator can be used for type arguments, yes. So yeah, you see here, you can use the underscore to infer a type of the argument when other types are explicitly specified. For example, you may have T is inferred as string, but some implementation derives from some class. Yeah, so runner.run. As you see here, you can T is inferred from string because some implementation derives from some class string, and then this you don't need to specify it because it's going to be taken from some implementation directly, which is some class of string. So it takes string directly without specifying it. That's the meaning. Okay, we are done with generics. I think the last sections were a little bit more advanced, and we don't need to cover them now very deeply. So thank you guys for watching, and I hope you have a nice evening.